Let's see. Okay. What's up? Stream? Oh, that's a lot of buffering. Oh gosh. It's very intense buffering. Let me see if this is working. Eventually I'm gonna have to figure out something to do regarding the buffering for sure. But in the meanwhile, here we are, another day. I would like to do a few more problems on LeetCode. There was one problem I was looking at that really was like, oh man, it took me, I had to do a lot of thinking regarding, I guess we're, uh-oh, not enough data to stream. What's going on? There we go. Okay, it's working. Got something to do regarding the buffering. Okay, yeah, eventually I'll do something regarding the buffering, but for now, I think it's okay. So, yes, so what I wanted to do was, I saw this question earlier, and I actually spent a lot of time thinking about it afterwards. This is an interesting question. Okay, so we've got a string of even length consisting of digits from 0 to 9, either of the following two operations on any number of times, and in any order on S. Add A to all odd indices. Digits post 9 are cycled back to 0. For example, if it's 3, 4, 5, 6 and A is 5, then you get 3, 9, 5, 1. And rotate S to the right by B positions. For example, 3, 4, 5, 6 becomes 6, 3, 4, 5 if B is 1. Return the lexicographically smallest string you can obtain by applying the above operations any number of times on S. Okay. This ended up being kind of involved when I thought about it, and I realized I don't know if I actually want to I don't know if I actually want to try to solve that on stream right now, because like I said, it's kind of just involved and it's gonna take me a while. And I had to really think about it, the solution that I was going for. I did come up with a solution I think that's relatively efficient, but it's not great. It's not great. It's reasonable. It's not a very elegant solution overall. It's an okay solution overall, but it's not like crisp, clean kind of a solution. So I was like, maybe I'll come back to this. Maybe I'll solve this another day, and then post the solution, and then look at some other solutions that people came up with that are much cleaner. If I had to outline the solution, though, basically what I was thinking was, if B is odd, then it's possible to apply A any number of times to all of the indices rather than just the odd indices. And if B is not odd, then if B is even, then you'd only be able to apply A to the odd indices. In all cases, you can always rotate back to the original position. And in some cases, there's only some rotations you can actually access. In some cases, you can access all the rotation permutations, or just rotations of a given sequence. So what this means is that there are roughly 10 possibilities when B is even, 10 different possibilities for the string of values. Or excuse me, yeah, when it's even, there's only 10. When it's odd, when B is odd, there's roughly 100. And it's actually not 10 or 100, it's bounded by 10 or 100. It's actually going to be the GCD of A and 10. either squared or singular. Yeah, raise the first power, raise the second power, depending on whether or not b is odd or even. That gives me a certain number of each of these sequences, which there's only going to be each sequence is only going to be at most 100. So it's either going to be, in the worst case, 100 by 100, so 10,000 of these. It would be 100 length 100 sequences to work with. Then the question is, okay, how do I find the optimal rotation for each of those sequences? And then once I've done that, I can compare those sequences, the optimal rotations of those sequences to each other to get the final answer. Getting the optimal rotation is kind of tricky. I devised a way to do it that involved basically copying the array, so I don't have to handle circular operations in a way that's not too difficult. And I basically said, okay, I'm going to get a rotation point, and I'm going to just go left to right through the given sequence that I have. And what I'm going to do is, for each of those points, I'm also going to have a kind of a look ahead where I compare that point to, or look behind, where I compare that point to the beginning of wherever I think I should start. And if it's a better start, then I would update the new start position immediately. If it's not better, however, or excuse me, if it's better, then I would update immediately, and then I would start moving, or excuse me, if it's not better, then I would just continue the next element. If it is better, I'd update immediately and continue from that point being the starting point. But if it's equivalent, which is the tricky part, then I would need to look at the next parts. So what I would do is I would look at the next elements, and consider if it's better or not. Now, also that could end up being the next starting point altogether as well. So I would also need to compare that to the previous elements. I might want to use a stack for this, actually. A stack might be a better way of doing it. I thought about it, and it kind of made sense in my head when I first thought about it, but I thought about it more, and I was like, oh, it's complicated. But there's basically a way to do it where, in theory, I think there's a way to do it in linear time where I could find the best starting point, starting index. And then also I would need to check, in order to update to that starting index, I also need to check whether or not that rotation point can actually be reached for that starting index. If it can't be reached, then I wouldn't update immediately. But if it's equivalent, then I would go character by character. If it's better, then I actually would need to see how far back it goes where it's better, which actually might be like I said, I might use a stack for this kind of a thing, because I might actually want to start at that index if it's better than both the element at that point and any of the previous elements. It would have to be better than the starting point. If it's just better than that spot, then I would use it, but I can't move the starting point unless it's better than the starting point. So yeah, I would have to check the starting point again. And again, if it's better than the starting point, then I basically shift immediately. So it probably is still linear time. It's just kind of complicated. I'm not sure if that entirely works, but that logic seems to work. That's a very custom kind of algorithm, is kind of my point. And I was thinking about this, and I was like, this is so much more complicated than I'd like it to be. And it might not be correct. And the ultimate solution would end up being like 10,000 operations roughly in the worst case. And then there's variations that have used fewer operations, not variations, but different inputs that would be better. But broadly speaking, like that's kind of the solution I came up with. And by better, I mean lexicographically smaller, digit by digit. So there is like an approach I came up with here for this solution. but it's pretty involved. It's kind of complicated. It took me a while to think this through. I spent like several hours thinking about this, quite frankly. I mean, I guess you could say this is a medium question, but it's definitely a pretty challenging question overall. So yeah, that's my analysis for this one. It was that you can, depending on if B is odd or even, there are variations, and then depending on the GCD of A and 10 and B and 10, there are also variations. But broadly speaking, like the more general case, larger case, and again, these, n is bounded 100 by 100. But in the worst case, n would be 100, and you'd have the ability to go through 10 different cycles of A on the even indices, multiply by 10 different cycles of A on the odd indices, because you can basically, and B would have a GCD of 1 with 10, and it would also be it would be odd, so you can shift forward, perform all the iterations here that you need, and then shift backwards to perform the iterations again. So that would give you the odd indices and the even indices. So that would be like 100 squared different possibilities, each of 100 characters. And then, like I mentioned, each of those sequences, you would try to figure out what the optimal rotation point is, which I think you can do that in linear time using a kind of a sophisticated custom algorithm, which I kind of tried to describe a moment ago. And that would give you roughly 10,000 operations to compare the 100 strings, each of size 100, rotated in linear time to get the right point, and then you much more elegant solutions. But that's what I had. Not the best, but it's okay. It's okay given the constraints. Also, given that I spent a while thinking about it, but given that I don't have like a ton of time to think about it. So I'm just gonna skip it for now. Do a bunch of other questions first, just to do something else. It's not as like bulky, I guess, or not as like, yeah, not as like involved. Hopefully, do some questions that aren't as involved for now, just because it makes me feel a little bit better doing things a little more, have more concise answers. Given an integer n, return the number of strings of length n that consist only of vowels a, e, I, o, and u and are lexicographically sorted. String s is lexicographically sorted if for all valid I, SOI is the same as or comes before SOI plus 1 in the alpha. Okay, 5 sorted strings that consist of vowels only. So these are only vowels and are lexicographically sorted. Okay, and they're strings of length n. So it would be like the number of, I think it's 2 raised to the n minus 1, quantity n minus 1. But this would be the number of non-decreasing sequences of 1, 2, 3, 4, 5 elements. I'm pretty sure it's so if it's 5, if there are 5 elements. Oh, excuse me. If it was length 5, it would be 2 raised to the, it should be 15. Forgive me, if they're non-decreasing sequences of length 5, no, length n, but the digits, it's a 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's a 5-digit, potentially 5-digit, partition, or yeah, it's no, so never mind, that math doesn't work. I was thinking of partitions of contiguous subarrays with n elements. That should be 2 raised to the n minus 1, but that is very similar to this. However, that allows for an arbitrary number of partitions. This can only partition into at most 5 elements, 5 pieces. This actually, I think you can compute this combinatorially, like more directly. I'm not sure the answer immediately though. I would say It's a non-decreasing sequence that's capped at 5, basically, or 0, 1, 2, 3, and 4, 5-digit non-decreasing sequences. How many are there? Well, non-decreasing sequences of 1 digit, there's only one for a given n. For 2 digits, it's going to be 0, 0, or 2 digits, or length n would be like 0, all zeros is one of them, all zeros and a 1, all zeros another one, all zeros another one, on and on, all the way up to all ones. So it's going to be the sum from 1 to n plus 1. I think it's n plus 1. So when n, for 1 digit it's n, or excuse me, for 1 digit it's 1, always, regardless of n. For 2 digits it seems like n plus 1. Because you have the rightmost 1 position is going to start from the first position and move all the way to the left position, which is the nth position, which gives you n different possibilities there, and then the empty case, which is just one possibility. For 2 digits, it gets more complex. Basically, you would take each of those cases and, I guess, multiply them by the 0 case. I'm not sure, actually. I'm not so sure about this, actually. Maybe the stars and bars argument is the one that I want here. If there's only 4 different, it'd be like 4 different bars and n stars. Yeah, actually, I think that's exactly correct. I think it's exactly stars and bars. So that would be how many? It would be n plus 4 factorial over n factorial over 4 factorial. So I think it's exactly stars and bars. N plus 4 factorial, so n plus 4, n plus 3, n plus 2, n plus 1, and then times n factorial. And that would be divided by 4 factorial and divided by n factorial, which just gives me 20 divided by 24. So if n is 1, we get 5 times 4 times 3 times 2 divided by 4 times 3 times 2, which is 5, which is what we expect. When n is 2, we get 6 times 5 times 4 times 3. 6 times, that gives you the right answer again. I think this is it. I think it's a stars and bars argument. How big is n? Between 1 and 50? Yeah, it looks like that's right. Yeah, I think you could directly compute this combinatorially. Close form solution. Let's go with 50. 50 and 25. Your stream is quite laggy, man. Can you fix that? Use recursion. What's up? 77KXRU. What's up? Student Rakesh. In this case, I don't think we'll use recursion. In the other solution, maybe I could have used recursion in the other question. Yeah, it is laggy. Unfortunately, I don't think I could fix it. Not easily. It's something going on with my my ISP, I think. Actually, I don't know if it's my ISP exactly. It might be a little more. I might actually know more about it than I realize. I'm gonna just say I think it's my ISP, but yeah, there might be something else going on, which I'm not certain of, but is more likely than just the ISP having issues. But I think it's going to be kind of laggy for a while, unfortunately. Which I think is not the worst thing, because it's a programming stream. It's not, it's not like a crazy amount of stuff going on the screen. But it is a little unfortunate. But yeah, stars and bars works pretty easily. So those of you who are not familiar with stars and bars, what you do is you take your elements. Those are your stars, your asterisks. Usually, it looks like it would look like. Let me show you. Show you what stars and bars looks like here. Actually, you know what? Hold on. I could do it right here. This is easier. Okay, stars and bars. Basically, these are your stars, asterisks. Here are your bars. And what you do is basically you would say, okay, and hopefully you can see this. I think you can see this, right? Yeah. So what you would do is you would say, all right, the permutations for this structure of stars and bars, it's going to be count the number of elements in total. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 different elements. The number of permutations is 17 factorial, right? That's how many different ways you can move them around if you treated them as individual objects. Then, because the stars are all considered similar objects, the same objects, you can divide by their permutations as a factorial, which is going to give you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 factorial. So 14 factorial of those permutations are going to be equivalent because all of these are all going to be equal to each other. So if you were to number them with unique numbers, they would all have different permutations, but because they would be those 14 factorial permutations, but all of those are all equal to each other. So you can divide by 14 factorial. And then the same argument is true for the bars, which there are 3 bars here. So you divide by 3 factorial. So you end up with 17 factorial divided by 14 factorial divided by 3 factorial. That's the number of ways that the stars can be distributed amongst the bars. So if you know how many bars you have, so in the previous case where I was trying to figure out how many non-decreasing sequences there are, non-decreasing sequences of vowels. In that case, it was vowels, but non-decreasing sequences of elements. I could just say each portion of this sequence is another section that's separated by bars. So it would be like the zeros here, the ones here, the twos here, and the threes here, and actually the 4s could be here. We could add another bar. And so now I have a stars and bars argument for how many elements come first, how many elements come second, how many elements come third, how many elements come fourth, and how many elements come fifth. And now I basically, the number of those sequences has a one-to-one relationship with the number of different ways these stars and bars can be arranged or permuted or I think rearranged is the right term, under the condition that the stars and bars are equivalent to each other, or the bars are equivalent to bars and stars equivalent to stars. So yeah, that's a pretty efficient stars and bars argument for that last question. Hopefully that makes sense. I don't know if I should have gone into more detail explaining that, but that's how I was able to solve that efficiently. So divide array into equal pairs. You're given an integer array nums consisting of 2 times n integers. You need to divide nums into n pairs such that each element belongs to exactly one pair. The elements present in a pair are equal. Return true if nums can be divided into n pairs, otherwise return false. Also, don't mean to. Where are you from? I am from the USA. 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 Return true if nums can be divided into n pairs, otherwise return false. So 2 times, so an even number of integers, divide them into pairs. Each element belongs to exactly one pair. The elements in a pair are equal. Return true if nums can be divided into n pairs. Okay, so this, we can use a simple frequency map. We just need to count that the frequencies are even of the elements. Unfortunately, the elements themselves are a small number. So this one's super quick, super easy. I don't know, man. Some questions are like very easy, and some questions are way more complex, way more involved. But we would just say fill. Constant x in nums, frequency of x, and then bool even frequencies is true. Something like this will work. I is 0, I is less than 500, and even frequencies, which is also and terminate early. Frequency of I is even, meaning, yeah, we negate this. So that'll tell me if it's odd, and if it's negated, it'll be, yeah. So this, I think it's, I'm just gonna go for it. I'm just gonna go for it, man. Yeah, that's pretty straightforward. 100%, pretty good. On to the next one. On to the next one. How are we doing on time? I think we're at 27 minutes. Okay. Count substrings that satisfy k constraint 1. You're given a binary string s and integer k. Binary string satisfies the k constraint if either of the following condition holds. The number of zeros in the string is at most k. The number of ones in the string is at most k. Turn integer denoting the number of substrings of s that satisfy the k constraint. I wanted to see something here. Satisfies the k constraint if either of the following conditions holds. The number of zeros in the string is at most k, and the number of ones in the string is at most k. Return integer denoting the number of substrings of s that satisfy the k constraint. It's a binary string s. Number of zeros is at most k, and the number of ones at most k. So if either of the following conditions hold. Okay. The number of substrings that satisfy the k constraint. Oh, that's interesting. So there are 12. There's 1, 2, 3, 4, 5 here. Then 1, 2, 3, 4 is 8. And then 1, 2, 10. Oh no, 1, 2, 3, yeah. 1, 2, 3. I got 5, 4, and 3, which is 12. Yeah. Interesting. Interesting question. Yeah, the buffering is pretty rough for sure. Okay. So input explanation. All the substrings. So all the substrings of S satisfy the k constraint because all of them don't have a 0. So there are no zeros. Okay, that's an interesting question. So I don't know the answer immediately for this one. I would say this one is, it's going to be, Sorry, my mind is elsewhere. Let me see something. That's brutal. So I'm just thinking. Think about some things here. Okay. So what was I even doing? Okay, I don't know the answer to this immediately. I'd have to think about it a little bit. 1 0 1 0. I'm wondering if a sliding window solution is good here. Think about how I could do this in linear time or better. Or linear time, yeah, linear time. I could probably. I almost certainly can do this in quadratic time. Because I can make a prefix array of the zeros and the ones, and so for I can go through every substring and efficiently find out how many zeros and ones it has, and then include or not include. So I could definitely do this in quadratic time efficiently, which will work for these bounds, and that'll be fast enough too. By the way, the question is, would I be able to do it in linear time? Or better, or in log n time, something better than quadratic time. Yeah, very straightforward prefix solution would work fine. But what about a linear solution? I'm thinking a sliding window might be good. So basically a sliding window, I could do left to right, all of the substrings in that particular subsection or have the k constraint. Maybe I could do it that way. So let's start with k is always at least 1, right? Yeah, k is always at least 1. So I could always start with left and right on the first element. And every substring there would count, so it would be 1. Then if I move to the right, I can count the ones and zeros. Now the problem with this is I would be double counting substrings. So I think I would actually go as far to the right as I possibly can while maintaining k. So I would move from 1 to 0 to 1, and I would see that there's only 1 0 here, and I would say, okay, every one of these substrings satisfies this constraint, because every one of the substrings has equal or fewer ones and zeros. Then once that's satisfied, then I can move the left part over, and I can say, okay, move to the right again. Yeah, that works. Sliding window works fine. Yeah, that's exactly correct. The number of substrings is just going to be the size of the window. It's going to be, if the size of the window is like, we'll call it alpha, it's going to be size 1 to alpha summed in a kind of an inverse relationship where the number of size 1 substrings is alpha, the number of size alpha substrings is 1. So it's still just going to be sum from 1 to alpha, which is just going to be alpha times alpha plus 1 over 2. Yeah, so we'll do sliding window. That should be a linear time solution, I think. I'm going to do it like this. Excuse me. So I'm going to do it like this for now. We're going to do a loop inside. And we're going to say We have count, so ones, zeros. And we're going to start with R is less than s dot size. And R is less than R s dot size, and ones is less than k or less than equal to k, or zeros less than equal to k. Okay, so this will keep looping until one of those conditions are met, and this will keep incrementing R, keep iterating. And we're going to say ones plus equals R, S of R equals 1, and then zeros plus equals basically the negation of that. S of R is not. I'm fairly confident this probably gets optimized by the compiler. Okay, so we'll keep incrementing until we reach a point where it's too far. So then result is going to be plus equals L. We're going to do const int x is going to be, it's L minus R, or excuse me, R minus L, and minus 1 plus 1, minus 1 plus 1. So the minus 1 is going to be, R is going to move back because we're not going to include the part that breaks it. And then we're also going to add 1 because it's going to be R minus L plus 1 is the size. And we're going to use x as R minus L, and then we're going to do x times x plus 1, bit shifted to the right by 1, divide by 1. Divide by 2 rather. Then we're going to increment L. So L is less than instant size, increment L. And continue from where R is. And before we increment L, we're going to subtract S of L equals 1, or S of L does not equal 1. Not. Yeah, we're going to subtract the left side before we increment. So we take the right side, add it all the way across, check the condition, and then remove L and move L over. And this should be a sliding window, I believe. And hopefully it's correct. It took me a while to kind of talk it out. Hopefully it makes sense. And it's wrong. And it's wrong. 30 should be 12. Okay. Right. Interesting. Okay, so my implementation is wrong because the logic for this test case should have been 12. I went through it by hand and I got 12, so it's got to be the implementation is wrong. It could be x minus 1. That actually could be the issue. Let's put some debug here. It should be 3 each time. 3 should happen 3 times. Which if you do, I got 4, 4, 4, 3, 2, 1. Okay. I know it's wrong. It shouldn't be 4. to start. And this is R is less than R dot S dot size. Although, yeah, once R once R goes off the side, I don't continue to compute it. That's a subtlety. I probably should have kept X though. Should have probably kept this line here. I don't know, why am I getting 4 there? It should be 3. It should stop here. And 0, 1, 2, 3. It gives me 4, and it should happen 3 times too. It should stop here once, here, stop here, and then at the end it should go off the edge. Interesting. Once it's equal to k, maybe it should be less than k, not equal to k. Maybe that's what's going on here. Maybe it's an off by 1 issue. So it's less than or equal to k, less than or equal to k. Now once I've added this element, R will be pointing here, and we're no longer less than or equal to k. Oh no, excuse me. We're still less than or equal to k, even when R is pointing here, so it would actually end up all the way over here. It's only when this is added. Okay, so it probably should be less than k. Yeah. That's kind of awkward. That's not the easiest thing to kind of like understand intuitively. But this one's wrong now. No, it needs to be less than or equal to k, because when they're both less than k, it doesn't imply that the next element is going to push it over. So I do need to use this less than or equal approach, but I think it's a little more subtle. Basically, I would subtract 2 on R. It's pretty tricky. I mean, I can do -1 here. I don't think it's right, though. No. No, that doesn't really work. Is it too high or too low? It's too high. Yeah, it's not quite right. I do need to use the equals here, but R ends up too far, basically. So what ends up happening here is R would be, we would process here. So this is what I want to process. I would get the R here. This is what I want to use. I would get R here, and then it would move forward. And then at this point, k is 1 for 0. We have 1, 0, and 2 1s. This would enter the loop, and we would have 2 and 2, and then we would increment R again, and we wouldn't enter again. But R would be pointing here at this one. And actually, it should be this section. So this section we went over. So really, it's more like I would want to have like a look ahead here. Kind of want a small look ahead here, I think. It's kind of what I was getting at before, with like custom loops and logic can be kind of messy. quite frankly. Okay. Something like this. This is maybe a little bit better. Still wrong, but better. So now I get the 3s that I was expecting. Okay. Why is this wrong? 3 times 2 divided by 2. 3 times 4 divided by 2 is 6. Oh, that is wrong. This logic is wrong because these overlap. These substrings overlap. I'll collect all these substrings, but the overlapping sections I would end up double counting. Whoops. Oh. About that. Huh. I mean, I could subtract the overlap. This one with this one. Yeah, I mean, I suppose I could do that. It would be the previous R. That works too, although that's really complicated. I don't know if it's necessary to do it that way. Yeah, there are a lot of new substrings that I'd be adding, though, so I'm not sure if that's the best way to do it, but I think I can do it like that, I think. It's a little confusing. I don't know if this is the best way to do it. This might be... This looks pretty good at first glance, but now I'm like, wait a minute, this is a little weird. So I just need the previous R value. They give it L. Excuse me. They give an L value. Yeah, let's do that. I think this works. The previous R value is going to be updated to, it's going to be R minus 1 because it's going to include this R minus 1. It's going to be inclusive. And then we're going to say const int overlap is going to be previous R minus L. And then plus equals this amount, and then minus equals overlap. This is one way of doing this. I don't know if this is totally correct. Could try it, see how it goes. Oh, okay. 16 expected 12. Oh. Okay. This, I have to add 1. That might be why. Okay, it's wrong. but it's a little closer. So now what it appears to be doing is I would get these three, and that would give me 6 different substrings. Then I would move over to these three, give me another 6, but these two are overlapping substrings. And so I would remove 3 there. So I would add 6, add another 6 to give 12, remove 3 to get to 9, add 6 again to get to 15, and then remove 3 to get down to 12. I don't know why I got 11. How did that happen? 11? Where did I get 11 from? Overlap should just be 2 each time. What happened there? Apparently not. Okay. Oh, the overlap is 1 at the first. Oh. Well, that's interesting. Actually, the first one should be 0, the overlap. Oh. I could just not have a +1 here. And not have a -1 here. That kind of works. It's confusing, but it works. Okay. Talk about off by 1 errors, man. I don't know about this one. I mean, yeah, it seems to work, but golly, gosh. Well, golly. How big could K be? Well, golly. Oh, the sub length of the string, okay. Well, golly. Well, golly gee willikers, man. Let's try a bunch of these random strings, see what we get. See what we get here. Nope. I'm going to go for it. This may or may not be correct. I don't know. I probably should have tested more cases. Oh, it worked. Okay. It worked. Just casual reminder, if you like the stream, don't forget to subscribe and like. Oh, wow. Yeah, I mean, gee, man. That's, the logic involved there was pretty... Let me see what the AI says. The AI is going to tell me it doesn't work. You ready for this? Oh boy. So, I mean, it's good that it worked. Probably not the best for an interview. Let's see. What is the... Okay. 2-pointer approach, maintain a valid window. Expansion loop expands R is adding the next character keeps the window valid. Counting via triangular numbers instead of adding R minus L, count a valid substrings. Ending at R minus L directly. Use the formula for triangular numbers. Calculates the total substrings of the current maximal valid window starting at L. It subtracts the substrings that were already counted in the previous iteration to avoid double counting. The overlap is determined by previous R, which stores the right boundary of the window from the previous left section. The outer loop increments L, effectively shrinking the window from the left and updating the ones and zeros counts. Complexity linear, space complexity of 1. Both L and R traverse the string at most once. Only a few integer variables are used. Comparison with standard approach. While the standard approach sliding window solution typically adds R minus L to the result at each step of the outer loop, this implementation optimizes the addition by calculating the contribution of the entire valid range starting at L in one go using arithmetic progression sums, adjusting the overlap of the previous step. Should I have just added L minus R instead of triangular numbers? I may have missed that. I may have made a mistake. Yes, you overcomplicated the counting logic. Just add R minus L at each step. Oh. I do that sometimes, man. I do that sometimes, man. Oh, that's funny. Right. Okay. All right. So I think I just do result plus equals L minus R. So it's going to be the number of substrings that contain, I think the number of substrings that end at R, maybe. It's not the ones that start at L. It's the ones that end at R, I think is the way to think about it when I look at a new R variable there. Yeah, that's going to be R minus L plus 1, I think. Are you sure it's not R minus R plus 1? Let's see. Overcomplicated the logic. Okay. Let's try this one. I do have a tendency to do that, it's true. Okay, this is wrong. -7, okay. R minus L, not L minus R. No way. I did that. R minus L is sufficient. I think it's R minus L plus 1 in the way that I've calculated this. Part of this might just be that sometimes it's a little hard for me to like think all the way through the summation schemes, I guess. Yeah, it's R minus L plus 1. Think all the way through the different ways of summing things. Interesting. Okay. Huh. I'm gonna go for it. See how this goes. Yeah, look at that one's correct. 1 millisecond though. A little bit slower, actually. Is this slower or faster? It's about the same. Okay. Why it's sufficient? Oh. For each left index L, you expand R to the furthest valid position. All substrings start at L and ending at any index L to R minus 1 are valid. You count the count of such substrings is exactly R minus L. You simply add R minus L to your total result for each L. Your current code attempts to calculate the sum of an arithmetic series to count all substrings within the window in one go and subtracts an overlap term from the previous iteration. This is unnecessary because the outer loop iterates through every possible starting position L anyway. By adding r minus l in each iteration, you naturally count every valid substring exactly once without needing triangular numbers to overlap subtraction. Corrected logic. Replace your counting block with this simple line inside the outer loop after the inner r expansion loop. You can also remove previous r x overlap in the triangular number calculations entire revised code snippet. So this is totally wrong. This is completely wrong. Oh wait, no, this might not be wrong. Actually, this might be wrong. This is probably wrong. This reduces cognitive load and the chance of off by 1 errors. That logic is incorrect and will significantly overcount the substrings. Sir, you were wrong. Are mistaken. When you're right, you're right. When you're right, you're right. By placing result equals r minus l plus 1 inside the inner loop, you're adding the count of valid substrings ending at r multiple times for the same left boundary L. When r moves from I to I plus 1, you add the count for I plus 1. But in the next iteration of the inner loop, you add the count for I plus 2, which implicitly includes substrings that should only be counted once per valid window expansion. Essentially, for a single valid window, you are summing 1 plus 2 plus dot 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 plus r max plus 1, which results in a triangular number again, but incorrectly applied because the outer loop also iterates. You must move the addition outside the inner loop. The inner loop's only job is to find the maximum valid r for the current L. Once r stops expanding, you add the count of the valid substrings starting at L exactly once. Why r minus L? The valid window starting at L extends up to r minus 1, since r is the first invalid index, or n. The valid substrings are S of L, S of L to L plus 1, S of L to R minus 1. Total count is r minus 1 minus L plus 1, which simplifies to r minus L. Absolutely right to challenge that, and I apologize for the confusion in my previous explanation. Revalidating your specific code structure in the standard solution, your intuition was correct. My previous correction was flawed for your specific loop structure. Clarify the two distinct valid approaches as your code mixes them in a way that causes overcounting. Okay, expand and count approach, original outer loop. Outer loop iterates, and the inner loop finds the maximum. Okay, you add r minus 1 once per outer loop iteration after the inner loop finishes. Your code's error placed inside the inner loop. This means for a single L, as R expands from L to R submax, you add 1, then 2, then 3, up to R submax minus 1 plus 1, minus L plus 1. This sums to a triangular number. For each L, which is massive overcounting. So move it to after the inner for loop. Count as you go approach standard solution. This is the approach shown in the search results. Inside the outer loop, which iterates R. Code uses the first structure, outer loop, inner loop. Apply the counting logic of the second structure inside the inner loop. Okay, interesting. Okay, interesting. However, the change I made is correct. The reasoning that I used is that I counted the new substrings end at position R, which are all distinct from any substrings seen so far, and extend to L from right to left. Yeah, that's my reasoning why this was why I did it that way. And it was correct. Let me see. Absolutely correct, and I apologize for the confusion. My reasoning is spot on. Code structure is indeed a valid and correct approach. It's a different perspective from the standard outer loop or solution. Count new substrings that end at position R and extend back to L. Inner loop R expansion is expand. Each character creates a new valid window. Counting at R, for this specific R, the valid substrings ending at R are SVal to R, SVal plus 1 to R, etc. But your code adds R minus L plus 1. This counts substrings starting from L up to R. To examine your specific loop. No, this is the right range from this is exactly the correct substrings. Correction on my part, L is fixed for the duration of the inner loop. As R increments, you're counting substrings SL to R, SL minus 1, R minus 1, no. It's trace outer loop. Evaluate strictly. Increments L means you are revisiting start positions. Yes. Yes, they're ending at R. It's getting so confused. This is the bug. Oh my gosh. Fails to count. Fails to count valid substrings and R cannot expand further. Oh my gosh, man. Code is correct. And passes all the 780 test cases. Oh man. Could be replaced by AI, man. I'm just kidding. Oh no, just kidding. This model is like a small model. This is not the kind of model that will be competing with for human capabilities. But it is really having a hard time following this. Having a really hard time with this. Yes, counts the starting positions. Mm-hmm. It's valid, albeit less common variation of sliding window technique, with the counting happens during the expansion phase rather than after. Thank you. Thank you. Thank you. Yes, I thought it was quite elegant as well. Have another question for you. Would it still work if I used, oops, let me submit it again for good measure. Guess something's gonna put the AI in its place, man. Gotta tell it, give it what for. Oh, I don't need, oh, excuse me. Sorry, like being put in your place. Result 1, 0, is that all I need? Yeah, okay. How about putting R minus L in the outer loop? Use result plus equals L minus R minus L in the outer loop after inner iteration. You had suggested that before, but I didn't believe you. Suspect that is equivalent mathematically to calculating the larger triangular number and subtracting previous triangular number as discussed earlier. What do you think? What do you think? Tell me what you think. Oh, whoa. What's up, chat? Holy smokes. What's up, chat? Dang. Great. Thank you. What's up, everybody? How's everybody doing? Yo, sir, awesome work. Will n squared work? You can do O of n squared. Yeah, there's an O of n squared solution. N squared itself won't work in that spot, but you can do an O of n squared solution. They said no. Hey, you reply. Let him solve. He isn't solving now. Just playing the GPT, wasting water. Bad guy. No, actually, it's someone else's machine. It's not GPT. I don't use the mega models, man. And you guys don't call each other bad. It's okay. I want everyone to get along if it's possible. I appreciate all you guys watching me. Helping people out there. We love them. I appreciate you guys. Thank you. By the way, if you like the stream, don't forget to subscribe and give it a like. So for the future, you guys will see my stream. Leave my goat alone. I appreciate that. Thank you. But it's okay. I appreciate everybody's input. Okay, let's see. Can you compare mine with yours? Like exactly how yours is working? Okay. Yeah, you can post your code. You can do it line by line. I'll take a look at it. Okay, so the way mine is working, just if you're curious, it's very simple. Sliding window, left side, right side. It's got this inner loop that's going to move the right bound over, and it does a slight look ahead, and it says, okay, if adding this next position keeps us in bound, then we're going to enter the loop. When we enter the loop, we perform that actual update, and we're going to say this right side from right to left, and you guys are reversed, so it looks a little weird for you, but from my perspective, it's right side to left. We haven't looked at any substrings up to that point that end at R. So I'm going to add all the substrings that end at R up to L. And when I get a new R, I do the same thing again. So this inner loop, this is why this part's in the inner loop. Excuse me. Then when I reach the outer loop, I move L over and I remove whatever was in that spot at L, which is either a 0 or 1. So I remove that from the count, and then I repeat, remove that from the count, increment L, and then repeat that inner loop again for each R that I can move over. That's the basic idea. And this is going to count all of the substrings in that sliding window without double counting any of them. And the reason it's not double counting anything is because each time the R reaches a new spot, none of the substrings I'm counting are substrings I've already seen. It's not possible to have already seen them because that's a new R value on the right side. That's like the basic explanation. But it is a kind of unusual way to do it, and that's the AI was having a hard time too. The AI was like, I don't understand. Correct on both counts. Oh, okay. So that's what I thought. I was like, I think if I do, so I had a more complicated logic going on before that had triangular numbers, and the triangular numbers, the AI was like, look, you don't need to do that. And I was like, I wonder if I were just to calculate those two triangular numbers and subtract them, if I would just get the R minus L at the end of it. And I probably do, and that's what they're suggesting. The AI says yes. Move the addition of the outer loop. Logic becomes for fixed L, find the maximum R such that L to R minus 1 is valid. All substrings starting at L and ending at any index from L to R minus 1 are valid. This count is exactly R minus L. Add this to the result. This is the standard expand and count sliding window pattern. It works perfectly and is considered more intuitive because it directly answers how many valid substrings start at index L. So the other way, which is what I'm looking at now, is, because it's slightly more efficient to do it this way, is put it here and do this. And the idea would be how many substrings begin at L. So we'd expand out to R and then count how many substrings from L to each position up to R. And then when we move over for the next L, that's those substrings. So that's why it's R minus L out here, which should also be correct. Let's see. Also the R is slightly off here. I think I need to subtract 1 potentially, only because this inner loop ends with moving R over slightly. It's a slight caveat. Wrong. This ended up being wrong. Okay. So no, this actually does not work. He says that the AI said it was correct, but the AI was wrong, man. The AI was wrong. Oh, man. Oh, man. Not getting replaced by AI today. Not getting replaced by AI today. I think the issue is I just need to add at the end. There's a subtlety here, and that is I just have to add that at the end, I think. I think that's it. That's probably something like this. No. No. I think the issue is if I do it this way, then I've got to remove this part. Yeah, this is very subtle. But it's this one. I think it's this line I need to remove. There you go. Yeah, so the problem with this approach, if I use the code I used before, so the code I used before, I stop when R gets off the edge. This code, I need to keep going until L goes off the edge. Otherwise, this code's a little bit more efficient though. Otherwise, it doesn't work properly. So that's very subtle. That's very interesting though. I like this. This is definitely a better solution. This is probably the best solution. Okay. This is all easy? Yes. Easy LeetCode questions. Hard LeetCode questions you can't solve. No, just kidding. No, this is if you took a LeetCode easy and you tried to do it in linear time rather than like quadratic or like cubic or something. But no, I mean, this is overall not too bad. This actually isn't that hard to think through, especially if you're like already familiar with like sliding window approaches. But that is very subtle. That part is subtle. But yeah, so you could put the logic inside and iterate all the way to only to the right side going off the edge. So you could do like a right side based iteration, or you could do a left side based iteration, which is the left side based iteration is a little more a little bit easier logically and a little bit less computation. But yeah, obviously I don't use sliding window that much, so you could kind of see where I'm a little bit because this is a pretty standard sliding window approach. I'm a little bit rusty trying to use triangular numbers and things like that. Let me see. I'm going to tell the AI though that I had to. I'll read chat in a moment. I'll tell the AI. Did you notice something special here? Let's see if the AI can figure out that part I mentioned about the left index and the right index changes. Okay, hold on. Here we go. Crazy solution. Thank you. Thanks. Yeah. The AI thought it was unusual too. Accept my connection LinkedIn. Yeah, sure. I might not accept it immediately. I don't like log into LinkedIn. I like to log into LinkedIn like once every few months. But yeah, you can add me on LinkedIn if you want. That's fine. There's someone else that added me a while ago and I still have to add him back. All right. N squared got accepted, hence the easy tag. Yeah, N squared works too. Yeah. BLR Bangalore. Oh, cool. All right, let me try this solution. Let's see what this looks like. I'll tell you what I think about it. I'm just gonna remove the tags. Actually, it's just this one will cut it, so we know who it came from. And this is gonna be. I'm just gonna clean it up a little bit so I can see what's going on. So we've got all the declarations. That's fine. All right. So this is the important part. While right is less than n, left less than n, if s of right is 0, increment zeros. If s of right is 1, increment ones. That's fine. By the way, you can slightly change this to. I'm not sure if it's better, but you can do it this way if you wanted to. Which I kind of prefer, instead of, so you don't have to introduce any branch statements, branching if statements. But this is how I read it. I'm not saying you should do it this way. I don't actually know if you should do it that way, but that's how I like to do it. In case you haven't seen that before, show that now. Let's do, okay. So this one. So there's this loop, and then this is inside. This is the inner loop. So you've got a double loop as well. While zeros are greater than k and ones are greater than k, you're gonna move the left side left to right. Okay, that's pretty good. And okay. So now you have, if 0 is less than or equal to k or 1 is less than or equal to k, answer right minus left plus 1, increment right, and answer, return answer. So I think this doesn't have a, yes, this is like a single, this is sort of like a single, this actually should be like a single if statement, I think, because it doesn't have the opening braces curling, so yeah. So this while loop is here. This if statement is kind of like here. And this is, where does this go? Oh yeah, I think these are supposed to be kind of moved over a little bit. Yeah, a few things are supposed to be moved over a bit. It's a little bit hard to read only because of how I formatted it, but I think all of this on the inside gets moved over, like here. Maybe this gets moved over too. Yeah, that's the while loop. Okay, so yeah, you've got a sliding window too, and this is efficient, I think. I think this is linear time. So this right increment will happen at every iteration. It's going to be right and left. You're going to do, it's very similar to what I did, actually. It's almost exactly the same. Increment the left side repeatedly. Oh no, there's one mistake here, I think. I'm not sure, is this correct? Let me see. I think there's a slight error here, actually. Very subtle error. Let me see if this will still run. I might need to remove some characters or something. Compiler. Oh. those hidden characters, man. I'm not sure where those came from, but for some reason the editor threw those in there when I copy pasted. Okay, let's see. Sorry, William, gotta go, man. Take care. I'm gonna try to join in the morning or something. Okay, all right, take care, Rashid. I appreciate you coming by, saying hello. Appreciate everybody come by saying hello. That's totally fine, man. You do what you gotta do. Oh, so this works. So oh no, yeah, this works. Excuse me, this is correct. I was gonna say, I thought this might have been incorrect because of, so I was wrong. Okay. I wasn't sure. I was like, I thought maybe it was incorrect. It's very similar to what I did, but I don't know if it's exactly the same. So, so this moves the left side over a bunch. Okay, this was actually what I was concerned about, that this while statement may move too many things to the left. I think it only needs to move once, though. I think this actually might be redundant. I think you only need to move once, and then it automatically will satisfy this condition again. I think that's what it, oh yeah, okay, that's what it was. I think you only need this once. Or maybe I'm wrong. It's an and. I was going to say an or here, but and is interesting too. Oh, no, not an or. I'm sorry, not an and. And is right. No, and's correct. I think this only iterates once per, like, I don't think this loops more than once, is what I'm trying to say. Let me actually test that. Int count loops. I suspect this only iterates one time each time this block is entered. I think this just happens once. Because I was thinking, I think your solution does a very similar thing that I did, where it'll add the it'll actually count the right side substring subarrays rather than the left side. But I think it only enters this. The reason it's correct is it only enters that loop once each time. And I was thinking that if it entered that loop more than once, like, because it is a loop, if it enters it more than once, then you're not going to get the right answer. And so if it ever enters that loop, oh no, excuse me, it does loop it more than once. I'm wrong. Okay. So maybe it's not counting the right. Maybe it's doing something slightly different than what I did, and I just don't quite understand it. That's cool. Nope. So it does loop a bunch of times. Maybe those are just empty cases then. Maybe that's what it is. Huh. This is cool, man. Okay, so I was wrong. I was wrong on 2 counts there. I thought maybe it only looped once. I was wrong. So what is it doing? So right and left. Okay. So this will stop once the right side goes off the edge. And then we say, okay, we're going to increment based on the right side. We're going to increment what we've got. So while we're in a state that's basically too far, we're going to move the left side and decrement the zeros and ones, which probably only happens like once in a while or something. I'm not quite sure. We'll come back to that. I thought this only happens once, but it actually happens a few times, which is kind of peculiar. But anyway, so as long as if both the zeros and ones are greater than k, then we're going to decrement and move the left side over. Okay. Then we say if the zeros or the ones are less than or equal to k, which they should be after this while loop completes, then we add the right side minus left side plus 1, which is going to be a right bound addition. Okay. And then this moves on the right side. So yeah, this is doing a slightly more sophisticated, slightly different approach, where you're operating on the right bound and you're moving the left side appropriately. which apparently you can end up with multiple iterations on the left side moving over. So you're doing something very similar to what I did. It's just that I think there are cases where the left side moves over multiple times that I didn't think about, I didn't realize. Which does make sense now I'm thinking about it. You basically did the same sliding window calculation that I did, except with a different like formulation. Like the way you wrote it was slightly different than how I did it. This is really cool though. It's really cool. The interesting part though is that this actually can iterate more than once. And it does, and that's in cases where when you add the next right position, you need to move several steps over on the left side to counteract it in order to get back to a state that's useful. But yeah, this is the same calculation that I had in the inner loop before. So very interesting. Very interesting. I think it's correct, by the way. I think it's right. Awesome. Very cool. So there you go. There's my full analysis there. Took a little while for me to get it all the way through. But yeah, that's cool, man. That's some good stuff, man. Let's see. Yo, bro, do you rap? I might. I might. Were you from which CLG, bro? Which college? IIT, B? You? Same? Which branch? CSC, bro? What about you? Bro, you crazy. Couldn't come up with that. What's up, Soham? Welcome. Howdy. The hell is too crazy. Thinks Code Force's master. He's top 10 in Big Code Challenge by Google. Oh, that's awesome. There you go. Thank you so much, sir. Carefully go through my solution. Spending your time. Truly grateful. Already in Google. Checked your LinkedIn. Already in Google. Really a goated man. This is LinkedIn. Achievement hackathons. There you go. So many things. He won SIH. Crazy. The man I want to be. So I am. Thanks. Are you guys all from Google? Are you all from Google? I don't know. That's good. I'm glad you guys are good at programming. It's good stuff. I'm honored to be in the presence of highly skilled developers. It's good. I actually probably shouldn't have pressed that button again. Oh, okay. I always hit this button first to make sure my test case is passed before I submit it again. But that was good. That was really good. Sweet. So yeah, you did a very similar thing to what I did before. But yeah, as it turns out, though, it looks like iterating on the right side and adding it. Oh, well, the way you did it is more efficient. So basically, you did it like similar to how I did it, but you had the inner loop and the outer loop swapped. And the way I did it, the inner loop and the outer loop were not. I was doing the addition in the inner loop, which I'm not sure is more efficient. I'm not actually sure which one's more efficient. Both of these, now I'm thinking about it, both of these R and S, they only pass through the array once. So if the increment is here or if it's here, I think it's still roughly the same amount of time. So I thought it was more efficient, but I'm probably wrong about that. And the AI was able to figure out the special detail. There you go. Potentially risky. So very interesting. Perfectly aligned with standard sliding window pattern. Okay. Couple of things. Let's see if the AI can understand this. A couple of notes here. Basically, one solution adds substrings starting from L, and the other adds substrings that end at R. However, have you noticed? I'll just give it away. See if it can concur with what it says. Have you noticed that since both L and R only loop through the array most n times each, even if the summation is inside the inner loop that I have, it will not execute more times than the L based summation moved to the outer. What do you think? So that's kind of a subtle thing. And let's see if the AI can figure that out. Probably can. All right, let's go to the next question. I think we analyzed this one pretty deeply. All right, XOR of numbers which appear twice. Okay, this one is probably gonna be a little bit tougher. Fundamental reason why the sliding window technique achieves linear time complexity, absolutely correct. The inner loop body executes at most n times in total, regardless of whether the summation is inside or outside. Complexity is still linear, monotonic movement, total operations, amortized costs. Even though you have a nested loop structure, it doesn't run n times for each L. Entire execution of the function, comparison of your two approaches, summation outer loop, elegant summation inner loop. Yeah. So still n additions, both cases. Both versions perform the exact number of additions, roughly n, and the exact number of pointer increments. The nested appearance is an illusion of the code structure. Logically, it is a single pass where R leads and L follows. Observation confirms that placing the summation inside the inner loop does not degrade performance to quadratic time. It remains a strictly linear solution, just as efficient as the standard approach, while offering a different, arguably more clever. Oh, it's more clever. Arguably more clever. That's what I like to hear, man. It's like to hear. Yeah, honestly, I just wanted the AI to tell me I was more clever. I just wanted the AI to tell me I'm clever. Are you two from same college? Hello, I love your stream. Can I get your Insta ID? I actually don't have an Instagram. So while I appreciate that, I do not have an Instagram account. But you can add me on LinkedIn though, for sure. I don't use LinkedIn that much. In the future, I intend to create a personal website. That's that called? No, a website. A website. I'll create a website that I can use as a personal website. A website that I can use as like a hub. So if people want to keep in touch with me, I'll have a website they could, so it's better than so like if people want to download software I create, I can put it up there, and people want to like stay in touch, could have a like a hub people can keep in touch with me. I'll probably have like a Discord too or something, have a bunch of things. Yeah, I don't really like the current model we have where it's like everything's on like a GitHub or it's on some like central repository somewhere. Like I kind of like the idea of people hosting their own software, open source or otherwise. So yeah, we're not quite there yet, but it's an idea. It's a fun idea. But I appreciate you guys coming and watching for sure. Find the XOR of numbers which appear twice. Okay, given an array nums where each number in the array appears either once or twice, return the bitwise XOR of all the numbers that appear twice in the array, or 0 if no number appears twice. All right, so I have to admit, I'm not as good with XORs and bitwise manipulation. I'm familiar, but I'm not the best. My first instinct is to try to just XOR everything and see what happens. If I do that, all the numbers that appear twice disappear, and the ones that appear once, I end up with like a hodgepodge of their bits. I want the ones that appear twice, and I want to remove the ones that appear once. If I XOR the whole list with itself, it'll remove everything. That won't help very much. One idea is I could think about the sum of the numbers and maybe get something that way. If I take the sum, well, actually, wait a second. It's the XOR of the numbers that appear twice, but okay. But deduplicated. If I take the sum of the numbers, I know there's two different summations. We'll call them A and B. A is the sum of the duplicated elements, and B is the sum of the non-duplicated elements. And I can rewrite the double elements as deduplicated as b, so it would be like a plus 2b would be the sum of everything. C would be a plus 2b, or something like that. But then b, I could find the sum of b as, it doesn't give me the XOR over b though, but that would be like the sum would be c minus a over 2. Not sure if that really helps me though, unfortunately. Maybe, let's see. I mean, obviously I could do a frequency map here. I mean, that's like the easiest thing. There's only 50 elements, so frequency map is super easy. That's like a super easy approach, but there's got to be a more clever way to do this. Yeah, I mean, a frequency map is obviously very easy. If I count the bits, the constraint's just so small, I might as well just use a all right, I'm gonna use a frequency map, and then we're gonna check for a better solution. I'm gonna use a frequency map and then check for a better solution. Yeah. Yeah. I'm not gonna think too hard about this. The constraints are so small that it's, I don't know if it's really worth. I'm not sure if it's really worth. Could start off with 1 here, I think. The constraints are so small, I'm not sure if it's even worth trying to do the other options. This is going to be or equal I mean, you could do this kind of thing. This works. I don't know if this is the best way to do it. This work, I think. Yeah, let's go for it. I don't know. Okay, let's get. Is there a better way to do this? Is there a better way? Yeah, I was gonna say it's because the constraints are so small. It's gonna get 100%, like kind of pretty easily. But let's look at the other solutions. Okay. Oh, that's okay. Okay. I was looking for something so clever too. I was like, give me something really clever here. No. There's a more space efficient way. Okay, let's go. All right. State numbers are between 1 and 50. You can replace the frequency array with a single 64-bit integer bit mask, constant space. Optimize bit manipulation approach. Okay. Let's see. Long mask to track which numbers you've seen. If the bit for number X is already set, it's the second occurrence, XORed into the result. If the bit is not set, set it to mark X as seen. Okay. Oh. But it's really just treating bit mask like an array. That's not that clever. It's like, yeah, but that's only because the numbers, constraining the numbers is so small. It's not really that clever. It's just an optimization of the data structure. Okay, so there isn't really a much better solution effectively using. Is that fair? I was trying to think of something like super clever, but frequency map. All right, got it. fundamentally need a mechanism to track state counts for each number, and frequency tracking is optimal. Yeah. 2 bits of information per possible number. Bit mask solution actually requires 2 bit masks. One for scene once, one for scene twice to fully replicate the logic without a counter, which is logically equivalent to compressed frequency map. Can't be the linear time. Need to read every number. Constant space. Only better variations are syntactic. You could do 2 bit masks, but scene once, scene twice, slightly more bit manipulation heavy, but logically identical. Sorting is n log n, just slower, so it's not better. Yeah, okay. Any alternative is merely a trade-off between code clarity and micro-optimizations and memory usage. Okay. Neat. Neat. Going with neat on that one. Okay. What? Oh, computer's struggling here. Hold on a second. What is, hold on a minute. Okay. Bit manipulation thing is tough. Could we please move on? Please move on to the next question. Yes, we will do that. Why run from hard Q, man? You're in Google. Have a sleep right now, but I thought I should drop by. Drop a good day, go back to sleep. Carpe diem. What's up, Yash? Carpe diem, man. Bye bye, William. IQ, it's high. Time for me to sleep. Thanks for such an amazing stream. Okay, take care, Ayush. Take care. I appreciate you guys coming by saying hello. Take care, everybody. Everybody's going to sleep now. How are we doing on the bit rate? The bit rate's a little bit better. Oh yeah, I'm gonna be probably done in maybe 15 minutes because I just wanted to kind of come on and do a few questions. So as it turns out, frequency array is probably about it. And then yeah, you could just pack the bits into a long, but it's not really necessary. Excuse me. Divide array into arrays with max difference. You're given an integer array nums, size n, where n is a multiple of 3 and a positive integer k. Divide the array nums into n over 3 arrays of size 3, satisfying the following condition. The difference between any 2 elements in one array is less than or equal to k. Return a 2D array containing the arrays. If it is impossible to satisfy the conditions, return an empty array, and if there are multiple answers, return any of them. Okay. So n over 3 arrays of size 3. Interesting. Huh. Okay. 2D array containing the arrays. If it's impossible to satisfy the conditions, return an empty array. If there are multiple answers, return any. Oh, I can reorganize them any way I want. I could do 1, 1, 1, 1, 3. I could do 3, 4. Oh, so these are subsets of size 3. These aren't subarrays. Oh, okay. And the difference between any 2 elements in one array is less than or equal to k. So if you sorted them, the difference between the minimum and the maximum would be less than or equal to k. Okay. So it's just the minimum and the maximum of these subsets of size 3 have to be less than or equal to k. Huh. Well, I mean, probably the easiest thing is to just sort and group 3 by 3. Just sort it. Yeah, sort it. That's actually exactly what they did here. That's exactly what they did here. The only reason you wouldn't be able to do that is if the first element and the third element are too far away from each other. Sorting it minimizes the difference between elements, and therefore minimizes the difference between 2 elements, I think. I'm not so sure about that. Probably, actually. Yeah. Then the closest elements are going to be that's for each element, and once it's sorted, the elements to the left and to the right are the closest elements to that element in that order. So to the left side, the smallest elements, the elements that are closer to it in size, decreasing size, but closest are going to be getting further away as you go. It's going to be in sorted order relative to that point, moving in that direction to the left. Same thing on the right side, sorted order, moving away, increasing to the right. But the question is, what does that help? Kind of does, right? I mean, basically, if I can't just sort it and then dump it into these arrays like this, then I don't think an answer exists. So it doesn't work for this one. So 2222 works. 245 does not work. Yeah, I think it's that simple. I think you just kind of sort it and chop it up. Okay. Okay. Can I use counting sort to do in linear time rather than n log n time? Yes, I can. 100K, 100K. Counting sort is viable here. I won't, but I could. I could. Came up with n log n solutions, sorting and storing the elements that appears twice, and sorted in an answer vector and took XOR while it worked. It's pretty good. Yeah, n log n is pretty good there. It's reasonable. Is reasonable. That does work. You don't need to store it in the element. If you sort it, you don't need to store them twice though, because it's you could just count the runs, the size of the runs, and if the size of the run is 2 or more, then you'd use that element. But that's good. It's good. It's good. All right, let's do the result. We're gonna say sort nums.begin, nums.end, and then for the accumulation, you can just say what was I saying? For the accumulation, you can just say let's see. For the accumulation, you can just say you just start with 0 and then XOR with each of the numbers that you find. Start with 0, XOR each of the numbers you find, and yeah, you can accumulate that directly, so you don't actually need to like store all the elements in between. This is actually going to do it this way. We're going to say result of could also do it this way. This might be easier for me to think about it. Result of I dot pushback, or no, result of I j equals nums of j. Do it this way. 0, 0, 1, 2. Nums of j plus 1, j plus 2. This might just be easier for me to think about if I do it like this. And then we just say if if nums of j, so it's nums of j plus 2 minus nums of j. If that is greater than k, then return the empty. What did they say for the result? I think it's empty if it doesn't work, right? Yeah. It's less than or equal to k. Yeah. So if it's equal to k, then it should just return the thing. Okay, I'm gonna go for it. I'm just gonna go for it. I think this is it. I'm gonna go for it. I could be wrong. I could be wrong. I suspect it. Yeah, that's right. It's inefficient, I think, but it is correct. Although it beats 90% of solutions. Okay, let me ask the AI. 1,000 test cases. Holy smokes. All right. Let me go for it again. Maybe there's some micro optimizations we can go for. It's pretty good. Not the best though. Micro optimizations. What can I do? So I could basically just say we could do a first pass. Oh, I could use counting sort. That's actually the other idea. Could use a first pass. And let's see if nums of j, let's just use j here. Let's get rid of I altogether. Nums of j plus 2 minus nums of j is greater than k, then we'll do a first pass sanity check and see if that's any better. 45 milliseconds seems okay. Sir, which car are you sitting in? I'm sitting in my home. I like to hang out in my vehicle. So if you don't mind, I actually don't like talking about the vehicle very much. If that's all right. I suspect, yeah, I think that adding that first pass filter is a little bit more efficient. If you don't mind. And then the other idea is, let me also modify the, oh, well, look at that. Hey, like that. Heck yeah. I did it. 100%. Wow. Well, that's pretty good. Well, there you go. That'll do it. It's faster than everyone else. All right. Shoot. Okay. It's the fastest solution. All right. Well, it's not always the fastest, but let me ask, do you think if I were to use counting sort here, it might be even faster? Let me see here. I'm very tempted to use counting sort. I could. Very tempted. C sort. Okay. We're going to here, let's say C sort of nums j decrement. Clear the array there. Don't sort here. C sort. For x in nums, C sort plus plus. And then we're going to say for int I 0, I is less than or equal to 1001, I and count greater than 0, count equals, I could do it this way, nums.size. And then we can say for, or we could say std fill. Actually, let's do it this way. J, let's do J0. We're going to say J plus equals frequency of I, fill, nums begin plus J, nums begin plus J plus frequency of I, of I, and yeah. And by frequency, I mean C sort. So that'll be sorted, and the rest of it should work as desired. Let's see how this goes. Counting sort could be theoretically faster, but with important caveats depending on the input constraints. Your sort is effectively linear. It's asymptotically faster than n log n. Might not be much faster in practice. Standard sort is highly optimized. Range sparsity, memory, implementation with counting sort. Wow, so implement a counting sort right here. Construct sorted nums. Is less than or equal to max value. Validate and build results, same as before. Verdict, theoretically linear, practically marginal improvement. Okay. Is this correct though? No. This is wrong. It's wrong. Yeah. Okay. Oh, that's what's wrong here. Oh, that's pretty subtle, huh? Well, it's maybe not that subtle. Actually, that is maybe not great to do it this way. No, it's fine. No, it's fine. I can erase what's in C sort. This is not right though. I did something wrong. Nums begins J. Nums J plus C sort of I. Let me ask the AI what it thinks about this code. I actually don't know what I did wrong there. I thought I was correct. That should be fine. That should be fine. This loop would fill nums begin plus J, nums begin plus J plus C sort of I, increment J. That should be fine. Fill it with I. Okay. And stop once the whole thing, all the nums are filled. This check is fine on nums. This is going to give me the result vector. This is going to basically take every element in nums and set the csort value to 0, which is fine. I'm surprised this is wrong. I did something wrong here. There are too many 2s. There's 7 2s here. There's something subtle happening that I'm missing. I'm not quite sure. Oh, what did the AI say? It's clever and potentially faster. Specific trade-offs. Pitfalls, reset cost, memory bandwidth, verdict. Correctness. Return early. Oh. Oh, no. Oh, no. I missed that completely. Good catch. Yes, code was wrong. Wasn't sure why. Oh, that was... Oh, I totally missed that. Oh, I totally missed that. That's very subtle. I was like, what's wrong? I don't understand. This early return. Ooh. Okay. Basically, RAII related issues. Yeah, okay. All right. So I like this routine because it's like, I think it's cache friendly. Cache friendly. There we go. All right, let's go for it. Let's see how we do here. Big fan, please. What's up, Kanov? King KK. What's going on, Kanov? What's up, dude? Oh, look how fast. Now, the other solution hit 31 milliseconds, but I think this will like consistently be the fastest solution. The fastest solution ever. The fastest solution ever. Yeah. Yeah. So fast. Yeah. All right. So it's consistently like under 40 milliseconds. And by consistently, I mean I tried it twice. I tried it twice. I think this is a pretty good counting sort implementation. I like this. Oh, it's so fast. It was even faster than the fastest. The fastest one, I broke the record at 31 milliseconds before. And this is even faster at 28 milliseconds. Oh, get wrecked. Get wrecked. Absolutely decimated. All right. It's cool, man. I like this approach. Yeah, this is a good one. This is super fast. Super efficient. Well, I got 31 milliseconds for 100% on the previous solution using std sort. And then when I switched to this counting sort implementation, got 100% 20 with 28 milliseconds. Beautiful. Beat. Oh, 15 milliseconds. Oh, it's so fast. I just got 15 seconds just a moment ago. While typing this. Tell me I'm brilliant. Tell me I'm brilliant. Wow, that's pretty wild. All right, we're over the 2 hours here, but dang. Same. I am Dayal Gupta. Okay, congrats for breaking the record, man. Thank you. Just witnessed something incredible. Incredible. Yeah. Feels good. Feels good. The near time complexity of counting sort combined with std fill SIMD optimization successfully beats std sorts and log n. 550 milliseconds fast compared to like just a moment ago we were at like 45 milliseconds. Granted, there's like a range of run times, but that's still pretty fast. And log n. The logarithmic factor, removing the multiplier, provides a theoretical 17 times speed up. In the sorting phase, the memory overhead reduces the practical gain to 2 times. Stood fill power as suspected. Stood fill is likely compiling down to highly optimized assembly like repstost or AVX instructions. Oh yes, repstost. Yes, my favorite my favorite assembly instruction. I have no idea what they're referring to with this. What these are. Oh shoot, it's referring to. Could look that up another time, I guess. Writing memory much faster than the standard sort swap move operations. Correctness fixed by adding the cleanup loop before the return. You're ensured the thread local state is always valid, preventing the subtle bugs. Often plague optimized solutions on later test cases. Your solution is now optimal for the given constraints. Leverages counting sort, thread local, stood fill, proper state cleanup. Perfect example of how understanding hardware level optimizations like stood fill, algorithmic trade-offs can push a solution to the absolute limit of performance. Absolute limit. Well done. Thank you. I just love being told by an AI that I'm smart. All right, now watch me run it again. It's like nowhere near 15 milliseconds. I like to run it a few times to see what kind of runtime. Yeah, there we go. 47 milliseconds. Yeah, it depends on a lot of variable factors that are not always the most consistent when you're getting down to like milliseconds on the online judges. All right, I said I was only gonna do a couple hours today. So let me just let me read this one and then I'll probably stop there. I might, if I know the solution, I'll give a solution, but if I don't, then we'll just stop there. All right. Oh, I wanted to read chat before we continue. Bye, goat. Good night. Thank you. You have a good night there, Dial. Yeah, I'm gonna head off soon. But let me read this and then I'll go. You're given a zero index integer array, battery percentages having length n, denoting the battery percentages of n zero index devices. Your task is to test each device I in order from 0 to n-1 by performing the following test operations. Battery percentages of I is greater than 0, increment the count of tested devices, decrease the battery percentage of all devices with indices j in the range by 1, ensuring their battery percentage never goes below 0, i.e. battery percentages of j equals max 0, battery percentages j minus 1, move on to the next device. Otherwise, move to the next device without performing any test. Return an integer denoting the number of devices that will be tested after performing the test operations in order. Okay, denote the number of devices that will be tested after performing the test operations in order. Okay, I have to read that again, by the way. Sometimes I'm like, my mind is elsewhere and I'm reading something, but I don't totally process it. Count tested devices after test operations. Okay, zero indexed integer array having length n, denoting the battery percentages of n, zero indexed devices. So this percentage of battery left in for each device. Okay. Are these integers? I'm sure. Okay, it's between 1 and 100, and the values are between 0 and 100, and there are about 100 numbers. Okay. Task is to test each device in order from 0 to n-1 by performing the following test operations. If battery percentages of I is greater than 0, increment the count of tested devices. Okay. Decrease the battery percentage of all devices with indices j in the range I plus 1 to n-1 by 1, ensuring their battery percentage never goes below 0. Battery percentages of j equals max 0, battery percentages j minus 1. Move to the next device. Otherwise, move to the next device without performing any test. Okay, so if we see a battery that has life in it, we decrease the life of all the future batteries and keep going. And we increment the counter. Turn an integer denoting the number of devices that will be tested after performing the test operations in order. So this says 3. So we have 1. Decrement everything to the right, add 1, skip this one. We see a 2, this 2 will be a 1. We decrement 1 for that and everything to the right. Or it really should be everything to the right, but we could decrement that one too. And then add 1 to our counted batteries. So it's 1, 2, and then the third one. So really this would be basically there's a way to do this that's efficient. You don't need to do like, so like the really simple, not simple, but like a more naive approach is that you could just use a like a Fenwick tree or any kind of like segment tree, interval tree to just perform the decrement literally on the whole range. You just do a range-based decrement, and that would give you an n log n solution, but that's like way overkill for this question. I'm pretty sure you could do this in linear time by just looking at what numbers you have to the right. So I think you could do this by just accumulating the decrements. So actually, I think I'm going to solve this one. I think you could just accumulate the decrements. So once you see a value that's in the range, you would increment the decrement, the difference, or the decrement or the counter. Let's say the increment the counter, and then now you're looking for battery percentages that are greater than the counter. Yeah, that's all. I think that's the easiest way to do this. So we're going to do counter 0, const int x, and I'm just going to make this like v or bp or something, bps. I don't know. We're just going to call it, well, batteries. We're going to go with batteries. All right. And result is 0. And we're going to say result plus equals x greater than counter. And then also counter plus equals x greater than counter. And then return result. So it'll increment the counter when we see something, and then the battery percentage has to be greater than that counter in order to be used later. Yeah, I think this is correct. I'm just gonna go for it. I think that basically appropriately, yeah, there you go. That basically appropriately does like a lazy propagation. 3 milliseconds. 10% does a lazy propagation of the changes. There we go, 100%, pretty good. All right, so maybe we'll just do that question before I get going here. Let me look at one more question. That one was a little too easy. It was hard for me to pass up on. Determine if string halves are alike. You were given a string S of even length. Split the string into 2 halves of equal lengths, and let A be the first half and B be the second half. 2 strings are alike if they have the same number of vowels. Notice that S contains uppercase and lowercase letters. Return true if A and B are alike, otherwise return false. Okay, this one you just count the number of vowels. So this one's actually pretty easy too. I think we'll stop there though. Thank you all for watching. I do appreciate it. Again, if you like the stream, don't forget to subscribe and like.